Hi everybody, welcome back to Food for Thought Physics. Today we are moving on from kinematics, the study of how things move, to dynamics, the study of why things move. We begin our study of dynamics by looking at forces. Roughly speaking, a force is going to be a push or a pull that affects the motion of an object. For instance, if there's a heavy box I want to move in my house, I would need to push the box and provide a force in order to get it to start moving. Alternatively, if someone throws a ball at me, I would need to provide a force while catching it to get it to stop moving. One important thing to note is that a force is a vector quantity. It has a magnitude somewhat clearly, and it also has a direction, as pushing something or pulling something in different directions have different effects on the motion of that object. In the year 1687, the great mathematician and physicist Isaac Newton published his book, his great work, the Principia, in which he used 3 laws to outline the fundamental nature of how forces work. Newton's first law stated that an object will remain at rest or remain at some constant velocity unless acted on by an outside force. Now, at first glance, this law doesn't seem to make sense. If I say throw something somewhere, then obviously its motion is going to change. And also it'll stop moving eventually, say if I push something too. However, this is because there are a lot of forces that in everyday life that we don't really see. For instance, if I throw an object, say, into the air, it falls and its velocity changes and starts going down because of the force of gravity, because gravity is providing some constant pull on this object. If I slide an object across the ground, it'll slow down and eventually stop because of the force of friction between objects. And these are all forces that we'll be looking at more in the future. However, as Newton and also Galileo before him imagined, in an idealized world where there's no friction, say in the vacuum of space, then an object that moving at a constant velocity, or say at rest, will actually stay at that constant velocity, or stay at rest, unless acted on by an outside force. So, technically, if you are somewhere in deep space, far away from anything, far away from other planets and stars and anything, and then there's no force of gravity and no force of friction, then you can probably test that this is indeed true, that these objects do actually stay at this constant velocity. This first law is also known as the law of inertia. Inertia is what we call this tendency of an object to stay at some constant velocity, at its current velocity. One important thing to note is that this first law, this law of inertia, actually doesn't always hold. In fact, all these laws don't always hold. They only hold in what we call inertial reference frames, which are very important. So I'll write it here. Inertial reference frames. And an inertial reference frame is simply a reference frame in which we are not accelerating. So, say if we're standing still relative to something, then Newton's laws do hold on whatever. And if we are moving at some constant velocity, then Newton's laws also hold. However, if say we are accelerating, then clearly we don't need any force to see something accelerating, because if something is at rest, say relative to the Earth, and we are accelerating relative to the Earth, then we would just see it accelerating without any extra forces needed. Newton's second law is what we will use most often. The initial statement of Newton's second law was roughly that force equals the derivative of momentum p over dt. And this quantity p here, this momentum, which we'll learn about more later, is going to be the product of mass times velocity. And technically we should put these vector hats on these. These are all vector quantities. So this momentum here is the mass times velocity. So what Newton said is that the force is actually going to be the rate of change of the momentum of some object over time. Now, usually, we can assume that mass is constant. The mass of most objects doesn't just randomly change. So we can rewrite this as force equals mass times dV over dt, because we can assume that this mass stays constant. And we know that dV over dt, the derivative of velocity with respect to time, is just the acceleration. So we can further simplify this into just force equals mass times the acceleration of an object, assuming that the mass stays constant, which it usually does. And this F equals ma is a more common form that you'll see for Newton's second law. Newton's third law states that if some object exerts a force on some other object, then the other object will exert an equal magnitude but opposite direction force back at it. So we can roughly write this as, say, if the force that object A exerts on object B, which we'll sometimes write as force sub AB, is some amount, then this object B will also exert some opposite force on object A, which we can write as the force sub BA. So we can write this roughly as the force sub AB, the force that A is exerting on B, is equal to the negative of the force that B is exerting on A, and this negative just reverses the direction of the vector, as we learned before. For instance, if I'm pushing on a table, I might be able to feel the table pushing back on me. That's the thing we feel if we say push on something. We actually feel the object pushing back at us. Alternatively, if you've ever been ice skating and you've been hanging onto the wall a lot like I have, you might notice, well, if I'm ice skating where there's almost no friction and I push against the wall while on my skates, then I'll slide backward, because while pushing against the wall is actually also pushing on me and accelerating me backwards in the absence of friction. That was a brief introduction to Newton's 3 laws of motion, which roughly define how forces work in this world. And these laws have been shown many times to be true in everyday settings. So in future videos, we can use these laws and some other things to look at many common forces and examples of forces that we'll see in everyday life and in many physics problems.